if I'm building a 50-story office building, I got to have plans. I just can't go to the hardware store and start buying wood and hammering the thing together. I need plans and electricity and plumbing and structural analysis and all that sort of stuff. Same for software. If I'm building a trivial piece of software, I don't need architecture. I just need to bang it together. And in fact, I can sort of immerse the behavior of the thing. But if I'm building a sophisticated piece of software, I need planning. I need architecture. I need to invest in some of those things. And so agility doesn't mean the absence of architecture. What it really means is fast feedback. How can I get the fastest feedback possible?
Hey everyone, welcome to Book Overflow. This is the podcast for software engineers by software engineers, where every week we read one of the best technical books in the world in an effort to improve our craft. I am Carter Morgan, and I'm joined here, as always, by my co-host, Nathan Toups. How are you doing, Nathan?
Doing great. Hey, everybody.
Well, we have another special episode for you guys this week. We're fortunate enough to interview again Neal Ford, this time for Building Evolutionary Architectures. We read and discussed Building Evolutionary Architectures over 2 episodes, and we also read and discussed over 2 episodes his excellent book, Fundamentals of Software Architecture, with Mark Richards. We interviewed both Mark Richards and Neal Ford for Fundamentals, and Neal Ford was kind enough to come back to discuss Building Evolutionary Architecture. Fantastic interview. Nathan, what do you think our listeners can expect?
Yeah, we got to really dive in on all the topics that we were excited about when we read the book. And it's always cool to see how he expands and gives us stories that are between what you could have picked up out of the book and some historical context on a lot of things too, which is really cool.
Yeah, not only does he talk about all of the concepts in the book, but even talks about kind of like the meta of writing a book, writing with different co-authors, how the book came to be. Really fascinating stuff. Neal Ford, such a delight to talk to him. And you get to some more backstory into the incident where Nathan somehow ran into him at a coffee shop in Germany. So, and we also find out why he always wears his red glasses. So please stick around. It's a great interview. This is Neal Ford as he reflects on his book, along with his many talented co-authors, Building Evolutionary Architectures. Well, Neal, thanks for joining us.
Thanks for having me again. It's always a pleasure.
Well, we're excited to have you back, our first repeat guest. And you and Nathan had a funny interaction in Germany, didn't you?
That's right. Yeah, we bumped into each other in a coffee shop, just completely randomly.
Yeah. I'm pretty sure I weirded Neal out pretty bad.
Well, so for those of you who've ever seen me in person, I have a very particular branding that I have red glasses and a red watch band and red sneakers almost always. And so it's really effective in a way of, sort of stamping me in public. So it makes me recognizable. So it's not the first time it's happened. I've been approached in random airports and other places too and recognized like that. It doesn't happen much, so it's still a novelty, which is nice.
Is that branding on purpose, or do you just like red?
Very much on purpose. I like red, but I realized, where that actually came from, this has nothing to do with the book, but I used to have a colleague who was a 6-foot-tall Swedish guy, and he used to always dress very goth, but he always wore like a Blues Brothers hat.
Oh.
And I realized how effective that was for branding, because when you walked in a room, if you were looking for him, you just looked for that hat and you could instantly find it. And I thought, well, I need to find some sort of identifiable branding thing. And I'd seen a pair of red glasses and I thought, oh, that's kind of cool. And so I sort of adopted red as my signature color for branding purposes.
Well, there you go.
It obviously works because, otherwise there's no way Nathan would have ever recognized me in a random coffee shop if I'd just been, mixed in with all the other Munich citizens.
It was so strange because, I was on a 2-week vacation. We were finishing up. I think it was like leaving like the next day or something. And I was like, this looks like the doppelganger of Neal Ford. And I was just like, if he speaks English, especially if he has a Southern accent, it's got to be Neal Ford. Yeah.
Well, we're excited to have you back. We had you the first time to talk about Fundamentals of Software Architecture, and then we read Building Evolutionary Architectures. Really, really enjoyed the book. We mentioned this, that this is the book that broke the podcast format. We've been trying to do around 200 pages a week. We took a look at this. We're like, what is it? Like 260 without the index? Like, yeah, we can squeeze it in. And we had to stop. We're like, this is dense. It's good stuff, but we're not going to be able to do this justice in a single episode. So we did it in 2 episodes, had a blast with it. We always like to ask authors who come on, why don't you set the stage for us? Just describe kind of what the computer science industry, I know it's a recent book, but what the industry was like when you decided to write the book and what kind of motivated you and your co-authors to write the book.
Well, there's actually a very rich history for this particular subject because so I agree with you that book is fairly dense and abstract. And part of that comes from one of the authors being a computer science PhD. It's Dr. Rebecca Parsons. So that's at least part of that is, due to her nominally writing in an academic style. But it is a, dense subject matter anyway. And software architecture books tend to be toward the abstract side as well. But there's a very distinctive evolution of this idea, which is a little bit tongue-in-cheek given its evolutionary architecture. Rebecca spent time before she joined ThoughtWorks working in the evolutionary computing space. We talk about that a little bit in the book. And when I first started working for ThoughtWorks, she was working primarily as an enterprise architect at that time. And we were having conversations about, I was actually doing a talk at that time called Emergent Architecture and Design. And as soon as Rebecca saw that the first time, she took me aside and very sternly, but in a friendly way, let me know in no uncertain terms that there's no such thing as an emergent architecture. That you can have emergent design, but you cannot have emergent architecture. And she made a really good point about that because, and we've since, sort of teased this apart further. Emergent design, so the example we always give is the one from the design community that you shouldn't start by designing a lorry. You should start with a roller skate and then a unicycle and then a bicycle and then a motorcycle, then a car, then a truck, then a lorry. You emerge the design as time goes by. That works great from a design standpoint. But that's really about the behavior of the thing. Architecture is really more about capabilities, security, performance, elasticity. That's why all the ilities are there. They are abilities. That's where the ility comes from for all these software architecture terms. And from a capability standpoint, a roller skate and a lorry are completely different things. Because a roller skate can't handle the same weight. They can't handle the same weight distribution. Everything about those things are different. And so you can evolve the architecture. It has to change at every stage along the way in a fundamental way, whereas design can kind of keep the same kernels and keep evolving forward. And not only did she convince me pretty well that there's a clean distinction between those things, she had a really good idea about how to manage the evolution of architecture. And this is this idea that's core to the book of the idea of an evolutionary architecture or an architectural fitness function. And she said the 2 words fitness function to me almost exactly 10 years before we published the first edition of the book, which came out in 2017. Wow. So it was 2008 or 9 when I first heard her say this fitness function thing. And it's like, ooh, what is that you're talking about? And we started having conversations. So we actually worked on these techniques for almost a decade on projects and in various ways until we finally decided we should write all this stuff down. And that's when Pat Qua came on board. In 2017, we published the first edition of the book. And then the one you just read is the second edition, which came out in the last November. We were asked by the publisher to come back and revisit it a few years later. That's my second edition, actually, was
really?
Building Evolutionary Architectures, second edition, yeah.
And that's when you added, am I pronouncing, is it Pramod?
Well, Pramod Sadalage, yeah. He has a tough name. And I had to learn how to say his name and my other co-author. So Pramod was also a co-author on Architecture of the Hard Part, along with Zhamak Jahakani, who has a Persian name. It's even harder to say than the Indian name of Pramod. But and actually, Pramod was there in the first edition. He helped co-author one chapter on evolutionary database design. But cool. We realized in the intervening time that you can't really isolate data in architecture to one chapter anymore. It's pervasive, and so realizing that, we invited him to say, okay, you should touch the entire book, not just one aspect of it. So that's he was informally a co-author to begin with, and we just formalized that relationship for the second edition. It just made sense.
What was it like working with so many co-authors? Because we read Fundamentals of Software Architecture, but that was just you and Mark Richards. So now you've got 4 people working together. How'd you manage that?
So it works pretty well. Most of my book projects, so I'm working on book number 12 now,
Oh,
and
wow.
I think 3 of them have been solo, and all the rest of them have been collaborations of one kind or another. In fact, the third book I ever wrote was a book called JBuilder 3 Unleashed. I don't know if you remember the Unleashed book series way back in the day. One of the contractual requirements for the Unleashed book was that it had to be at least 1,000 pages.
Oh, wow.
Because that's back before the internet, when books had to be these massive tomes. We used to joke that it wasn't a proper technical book unless you could stun a charging ox with it if it was coming at you. But contractually it had to be 1,000 pages, and one person can't write that much stuff. So that was a 6-person book project, and generally those are not fantastic. It's been my experience, because writing a book is a terrible ordeal anyway, and particularly for first-time authors, it's been my experience that almost always first-time authors, at least one of them, lose their mind at least partway through the book writing process, and so that causes problems. I'm really fortunate in that I've found a lot of really good co-authors recently. Mark is fantastic, and Rebecca, Pramod, and Pat Qua were also quite nice. But one of the great benefits that we have is that we are writing these for O'Reilly. And so we are using ASCIIDOC and a Git repository to store every single thing about the book.
Oh, wow.
So they use ASCIIDOC, which is basically a markdown-ish format, much rich enough to write a technical book, because I've written the last few in those, except Head First, which is a completely different animal. But it's a Git repository. So literally for the Building Evolutionary Architectures book, the 3 of us only met face-to-face one time in London.
Wow.
And we met for 2 days to establish the outline and that sort of stuff. And then the rest of it was done on Zoom meetings, and I flew to London a few times and met with Pat, and then I'd bump into Rebecca in one place or another, but we only met face-to-face one time. And we never met face-to-face for the second edition, because you can do it completely collaboratively through Git and through ASCIIDOC. And so I've really fallen in love with that particular writing mechanics. Word processors are toys when you talk about book-sized projects. And that's actually a deal breaker for me. If a publisher came to me and said, we'll give you $1 million to write a book, but it has to be in a word processor, I'd have to say, oh, sorry, I can't take that $1 million, because it's just not worth the pain and grief and agony. And of course, I'm a software developer at heart, so being able to use ASCIIDOC and text-based formats and Git and diffing and that kind of stuff is quite nice. And I've also built up these text-based utilities. Because it's all plain text, you can do magic stuff. So this is not from Building Evolutionary Architecture, but it's a great example of the flexibility. So in our book, Software Architecture, The Hard Parts, we have all these little vignettes scattered throughout the book telling the story of the SysOps squad, almost like a lightweight version of the Phoenix Project. Because we wanted, again, toward this idea that software architecture books are so abstract, you need something to kind of ground it. We use Penultimate Widgets in the Building Evolutionary Architecture book as our fake company to kind of ground them, in real examples. And we had all these vignettes that were scattered throughout the book, but we wanted them to read as a single narrative and make sense and be consistent. And so we built each one of the narratives as a little ASCIIDOC include, and then we built a synthetic chapter at the end of the book when we built it, which was just the vignettes in linear order, in the order they show up in the book. So we had one fake chapter at the end every time we built the book, which was just the story from top to bottom. And then when we were finished with that, we just got rid of that little part of the build, and it was gone, and they were just there where they live. So, the ability to manipulate the text programmatically is something that I've fallen in love with. And I've got a lot of little utilities I've written over time to deal with repos like that.
Oh, that's so cool. One of my favorite sections in the book was the Pitfalls and Anti-patterns section. I think it helped make it sort of more concrete. Especially, I learned a lot from the, the pain of others, I guess.
Mm-hmm.
I was curious, what what anti-patterns or pitfalls have you noticed that people get particularly stuck on when trying to use a evolutionary architecture patterns in their work?
The most common one probably still is trying to reuse too much stuff institutionally. It's just too tempting. I mean, we can't get rid of that code. We should reuse it somehow. But people say this to me all the time professionally. I keep getting people that say, okay, our aspirational goal, we really love, highly decoupled microservices and isolation, quick turnaround and all that stuff. So we really want that. But we also don't want to have to reinvent the wheel over and over. So we want to have a high degree of institutional reuse. So we want, highly decoupled architecture and high degree of reuse. And I have to be the bearer of bad news that you can't have both those things, because reuse by definition is coupling. So you cannot have a decoupled architecture and one that has a lot of high reuse. And that's still the problem that people fall into. And in fact, the good way around that is looking at reuse from a different perspective. Everything in software architecture is a trade-off. You remember that from the fundamentals book. And that's a great example of understanding what the trade-offs of reuse are, because it's the abstraction part is really good, but the downside is the coupling. And so then the question becomes, well, if I'm coupling to something, how can I not make it bad? And the answer is volatility, low volatility. So effective reuse is really two things. It's good abstraction, but it's also low volatility. Because when you think about it from an evolutionary standpoint, if I have this thing I'm reusing a lot and it changes all the time, everything's got to stop and coordinate around that change. Even if you're not breaking, I still have to check to see if I'm breaking because of that change. And so that's why candidates for reuse are both good abstractions and have really low volatility, which is why, and I love finding the root cause for the kind of common sense advice you constantly hear in software architecture. And this is a great example of one of those things about reuse, because you've always heard that, well, you shouldn't really reuse domain concepts much. And in fact, that's the whole premise of domain-driven design, is bounded context, isolation, don't try to reuse implementation details. Well, the reason for that is exactly because think about things that we really effectively reuse in software systems. It's plumbing, frameworks, libraries. It's technical things, not domain things, because what changes the fastest in the software system you're building, the thing you're building the software about, which is your domain. This is where that architectural advice from domain-driven design really comes from. Domain things are very volatile by their nature, because that's what you're building the software around, and therefore make terrible candidates for reuse. The solution to that is isolation at the bounded context level to prevent that sort of rippling side effect. So that's a great example of, a sort of casual advice you've heard in software architecture, but then figuring out, okay, that's why that casual advice is generally true in software architecture. But understanding that why is useful, because then it shows you places where you can, in fact, break it, because you know why you're breaking it and you can bend it rather than break a rule like that.
That's great.
You talk about the last responsible moment, right? And just quoting from the book, it says, the agile development world has long extolled the virtues of last responsible moment. Delaying decisions as long as you can, but no longer. Making decisions too early tends towards over-engineering, and too late leads to failure to meet architectural goals. How do you know when the last responsible moment is? How do you develop that intuition?
Well, that's the really tricky part, isn't it? That's exactly like the advice you commonly hear to embrace simplicity in your design.
Right.
Okay, sure. Be happy to. Exactly how do you do that? So that's the tricky thing about last responsible mode. That's what requires all the context. That's the thing about trade-offs in software architectures, knowing the context to know what to trade off. Because it's easy to do the analysis once you know what to trade off. Figuring out what that list is sometimes difficult. But the real secret to figuring out when that last responsible moment is really the secret to the intersection of agility and software architecture. So you constantly hear people say, oh, well, agility means no software architecture. And that's not correct. It depends on the scale of the system. So the common analogy I use for this is let's do the common tortured metaphor of building stuff. If I need a doghouse, I don't need an architecture. I need lumber and nails, and I can build a doghouse pretty easily without plans. If I'm building a 50-story office building, I gotta have plans. I just can't go to the hardware store and start buying wood and hammering the thing together. I need plans and electricity and plumbing and structural analysis and all that sort of stuff. Same for software. If I'm building a trivial piece of software, I don't need architecture. I just need to bang it together. And in fact, I can sort of immerse the behavior of the thing. But if I'm building a sophisticated piece of software, I need planning. I need architecture. I need to invest in some of those things. And so agility doesn't mean the absence of architecture. What it really means is fast feedback. How can I get the fastest feedback possible? And that's the secret to the answer to your question of how do you figure out when the last responsible moment is. Build a fast enough feedback mechanism so that it can tell you, okay, I don't think we can go much further without making a critical decision here that's going to take us down one path or the other. But get as much technical feedback as you can. And the mechanics of that, of course, is this idea of fitness functions in architecture. That one of the reasons that's so critical, particularly from an architecture standpoint, is that if you're building a new system, you have by definition never built that before. Because if you had, it's software, you just copy it and you got another one because it's all digital. So you've never built this thing, but you may have built one really close to it, but you've never built this one before, which means it's exploratory. Anytime you're exploring, you need ways to validate that you're on the right path as rapidly and as often as possible. That's really the feedback that you're getting. And that's the same for this idea of last responsible moment. You need that kind of feedback to go, okay, we have reached the point where I have to decide if we're going to split the database up or not. This is the point where I have to make a decision because I've looked at the trade-offs on either side, and this is the last moment that I can make that decision. But it's that constant feedback and, can I go another short iteration before making that decision and before moving on to the next thing? That's really key. I heard a great story that was told by someone who was pairing with Ward Cunningham, who, famous, there's a famous metric in the software world, used to be, is your Ward number, which is, how have you managed to pair with Ward Cunningham? And he tells a story of pairing with Ward in the very early days. This is in the very early days of Java, and they were trying to build something. And he was saying, okay, well, I want to do test-driven development, but I don't know how to start, simply enough. And he said, well, what's the simplest thing you could do? And he said, well, I need a data. He said, you don't need a database. You need data. So just serialize this object, and that's good enough to start with. And he's like, oh, yeah, sure, okay. And they did that. And it turns out that's the design that survived the whole thing because they never really needed a database. They had like 5 data items. So, you don't need a full database for that. I mean, putting it on a file system is perfectly fine. And they never had to revisit that decision because it never really came up again. So, that's one that they got enough feedback to say, okay, we don't need to revisit that decision. Now, if you'd normally been doing that, the first thing you do is find an industrial strength database. I have 5 things to store. Find me an Oracle instance, and get me a DBA and all that sort of stuff. But the last responsible moment says, well, you don't really need that until the feedback tells you that you actually need that. So I think that's part of the skill of becoming better at being a software architect in an organization, is learning where the trigger points in that organization that you're in really are. And how far can you push that without it becoming a detriment, which is always the problem of going too far and then having to backtrack some.
One of the big focuses in this book is not just on the architecture of the software, but also understanding how it serves the organization. And there's a concept in this book that I'd never heard of before called the inverse Conway maneuver.
Mm-hmm.
About teams that are structured to match the desired architecture.
Yep.
I wanted to know if you could explain sort of how you would apply that in practice, because this book was an aha moment for me in that I realized I was running into a strategy issue where culture eats strategy for breakfast, like the Peter Drucker quote. But anyway, I would love to hear more thoughts on the inverse Conway maneuver and how that made it into the book.
Absolutely. I can actually tell you the origin of the term. We produce this ThoughtWorks Technology Radar a couple of times a year. And one of the observations was exactly this inverse Conway maneuver. So first we go back to Conway's law, which basically, and I'm paraphrasing, says that when you have a communication structure within an organization, you end up designing things around that communication structure. The famous story is that Ralph Johnson, who's a famous, well-known architect, was just put in charge of this brand new large enterprise. And they said, well, what is your overall architecture going to look like? And he said, well, I don't know yet, but I know it's going to have 5 parts because we have 5 divisions. So I know it's going to be, I don't know what the 5 parts are yet, but I know what that's going to be. And so very often, the communication structure and the design mirror each other. That's basically Conway's law. What we realized, and that is so pervasive that I would be willing to bet that a large number of people who are listening to this podcast, even though they're in an organization where they're building microservices or cloud related assets, all the presentation layer people still sit together in one part of the organization. All the developers still sit in another part of the organization. All the DBAs all sit together in another, and the operations is somewhere else. That's the implied layered architecture. That's the Conway's law of, we're layered architecture. Let's split them all by technical responsibility. That's actually a really bad idea if you're doing microservices. And this is interesting because we're always thinking about new fitness functions. And one of the categories that we only brush against in the book is a process fitness function. And here's a great example of a process fitness function that shows you that you haven't applied the inverse Conway maneuver. How many JIRA tickets does it take you to implement a new feature? If it's more than 7, you've got Conway's inverse Conway maneuver problems, because you've got to create communication to create features. You either do that organically in the room or you do it with some mechanism like JIRA tickets. That's a common process fitness function for us. How many JIRA tickets does it take to implement something useful in this architecture? And if it's more than X, then that's a smell. That's exactly this kind of inverse Conway maneuver. And the person who coined that term actually is one of the members of the TAB at that time, Johnny Leroy. And he was actually, we referred to him, we always need clever names for things on our radar, and we referred to him as the Department of Naming because he could always come up with clever names for things. And inverse Conway maneuver was one of his. And Sam Newman almost instantly picked that up and put it in his Building Microservices book. Of course, we picked it up, which is a clever thing. Fortunately, though, and this is a great example of one of those things that we were sort of doing organically at ThoughtWorks for a while, and then somebody comes out and gives it a proper name, and it's like, this is the thing we've been doing forever. And the proper name is now team topologies. Inverse Conway maneuver has been eaten by team topologies. That entire book is exactly about what question you just asked. What is the impact of team structure on productivity and team partitioning and that sort of stuff? It's a much deeper investigation into that thing that we long suspected was really important. And in fact, it's interesting you brought that up. That was one of Pat Qua's big passion areas in the book, was the team and the process impacts of all of these things in software architecture, in addition to just the technical aspects. That was really the motivation for that definition of evolutionary architecture, that last part about multiple dimensions. Multiple dimensions meaning not just source code and not just data, but also things like process, things that touch on enterprise architecture, and a bunch of other touch points like that, because it can really exist in all different levels of your architecture, and even in places like process.
Have you ever seen the inverse Conway maneuver like fall flat on its face, or people blow up their team structure and just can't quite get everything to gel?
Oh yeah, absolutely. It's actually pretty common. And so I always tell people, the first thing you need is a culture for experimentation. Have a culture where you can experiment with stuff like that and actually get metrics to see if it works. Because regardless of what some book author tells you or some consultant or whoever else, it may not work in your organization. There may be exogenous forces that just prevent those kind of things from happening. So do the experiment on your own and actually do some honest assessment to see if you think that will actually work and benefit your organization. There are a lot of forces that might prevent that kind of restructuring from happening or being successful. So yeah, we've definitely seen that fail. One of the things you have to protect against, we used to, as an organization, do a lot of what we call agile enablement, where we would come in and work with teams and actually show them agile engineering stuff as we were building stuff and kind of upskill them at the same time. Uh, but we ended up stopping doing that for the most part. We still kind of selectively do that because we realized it took a lot longer to show somebody how to do something as you're doing it. And in fact, we did some post hoc analysis and started charging people double the rate if we were doing enablement versus just delivery, because it takes a lot longer to do that. But the thing that ultimately made us stop doing that, and the thing that I think defeats experiments like inverse Conway maneuver in too many organizations, is that anytime you change the way people work in a fundamental way, it's a very fragile change. And as soon as one little disruption from the outside world shows up, that change completely cracks and they fall back into the habits that they had before. Schedule pressure is the common one. Okay, let's reorganize our teams and get everything set up and it's nice and okay, everything's kind of working, and up schedule pressure, we have to have this done. Forget it. All the operations people, go over there and start working on that. So that's the common thing that defeats those kinds of efforts. And so it's really important as a leader in organizations like that to provide space so that things that will break that structure are not allowed to break the structure, or at least not permanently break it. Because once you've broken it, it takes forever to get, to rebuild that fragile new equilibrium back. And when it shatters, it takes a long time to rebuild that back up. And so certainly things around engineering practices and certainly things like team structure are very subject to those kinds of fragilities.
Let's see. I had a question at the tip of my tongue and it just got past me. So one of the things that was really cool last time we talked was how AI has creeped into so many parts of our lives. Have you seen any AI tools or patterns that have supplemented sort of the evolutionary architecture work that y'all have done?
Well, we've been using it for quite a bit and playing with it quite a bit. Is that it turns out ChatGPT knows about ArcUnit.
Oh, wow.
So you can tell ChatGPT, write me an ArcUnit fitness function that tests this thing, and it'll just spit it right out for you. So we've been using it a lot for generating fitness functions for various things. You frequently have to tweak it and change it and refactor it, but it's giving you the basis for it. So even if you don't already know some of the testing frameworks for structural testing and that kind of stuff, ChatGPT can go a long way toward helping you with those kind of things. But we've also seen much more sophisticated fitness functions around things like, so to give you two examples, one is AI pattern matching for packets at the network level, looking for anomalous patterns. It's not looking for a particular pattern, it's just looking for something unusual. So you can build up statistics for what does normal traffic on this network look like, and then suddenly it's way different. Raise a red flag. So we built several things like that for organizations around several kind of things like that. The other thing that we're seeing a huge uptick on is renewed interest in the sort of internal quality fitness functions, which, we talk about things like psychometric complexity and abstractness and instability and distance and main sequence. And we talk to that about developers. We kind of, we know we're supposed to do it. Yeah, that's fine. That's good. But now we're moving into a world where we're dealing with as much or more generated code as we are handcrafted code. And how do LLMs solve problems? Brute force. And so these internal code quality, structural fitness functions, I think are really important to wire up for generated code, to see if it's using brute force to solve some problem by building a switch statement with 50 different entries in it, which a human would never do, but an LLM would do in a heartbeat. And so psychometric complexity, coupling, some of those core metrics, I think it's really useful to look and build some safeguards around the negative anti-patterns that LLMs do when they generate code. So that's another place where they're coming handy. And finally, the third one, there's a whole new category of fitness functions that are necessary here. And this is one of my favorite ones that I've talked about in other places, but it's a great example of, the AI stuff is fascinating, but the second and third order effect stuff is even more fascinating. And so I mentioned our radar before. One of the things that we talked about a couple of radars ago are dependency checks for hallucinated dependencies as attack vectors. So here's the scenario. I tell ChatGPT, hey, generate me some JavaScript code using some framework. And, ChatGPT being very useful as part of what it does, it hallucinates some dependency that doesn't actually exist. Well, let's say it's a really common JavaScript framework and it creates that same hallucination a lot. And some nefarious actor notices that and puts a real dependency behind that hallucinated dependency, and now it's injecting malicious code into your ecosystem without you realizing it. So having some sort of fitness function wired into Dependabot or SNCC or one of those kind of tools that do software bill of materials, mark my words, those 4 words, software bill of materials, is going to become really, really important. Because the Log4j thing that happened, like a year and a half ago, that freaked a lot of companies out because the adults went to the software developers and said, tell me what's running in that piece of software. And the software developer said, beats me. Bunch of code, but I don't know what's in there. And they did not like that answer. That was not a good answer to that question, because increasingly we're going to see these kind of vulnerabilities come up in dependencies, whether AI generated or not. And so that, I think, is a whole category of fitness function we're going to see a lot more use for, is to make sure that we're not accidentally pulling something in that we shouldn't, and some safeguards around those kind of things. The last category of those things we actually alluded to in our first book. We can imagine, I haven't seen this implemented yet, but you can kind of imagine a world where you build pattern matching fitness functions to help you find brand new fitness functions that you didn't know you needed. So observe the usage of this architecture and tell me when things break. So a great example of this is in the second edition of the book. One of the things that we did was send out a solicitation to our coworkers. Hey, where have you used architecture fitness functions that you thought were interesting? Because we wanted a bunch of case studies. And one whole category that fascinated us was the using fitness functions as experimental media. Because so often in software architecture, I've never actually built this before. And it may be that no one on earth has built this particular system talking to this other system in this particular way. And you end up making a lot of back of the envelope calculations. Well, you build fitness functions to both validate those things and as a way to make sure that you understand what that thing is and keep that wired in over time. So that's another completely unique use that we had not thought of before that is really super useful.
One of the recurring villains in this book is coupling. And you talk about the dangers of tight coupling. Talk about, is it connascence or connascence? How do you pronounce that?
Connascence, I think.
Connascence.
I've never heard anyone who knows the actual root word say it, but I think it's connascence, yes.
You have a lot of great strategies for kind of how you can, once you've become tightly coupled, how you can work yourself away from that. But what do you think causes tight coupling in the first place? And what kind of attitudes do you think engineers could have to avoid creating coupling?
One of the most common things that we see, and in fact, I talk about coupling in this book, and in fact, the entire Software Architecture, the Hard Parts book, is really about coupling. The first chapter in that book is called Discerning Coupling in Software Architecture, because this is the thing that we have to deal with all the time in software architecture. But the most common place that I actually see people building headaches for themselves, this is one of those things where a lot of architects just sort of lazily default to things without going through the trade-off analysis, and it's around contracts. overspecified contracts lead to stamp coupling, which is a nightmare. So let me just show you what I mean by that. The stamp coupling is this idea of sending a larger data structure than you need because you want to send it to one service and it deals with the first part of it. The second service deals with the second part of it. And the third service deals with the third part of it. So these big, huge contracts that you pass around. The problem with those is that if any one of those services change, it breaks the entire contract. That's stamp coupling. The problem that I constantly see in architectures like microservices is that architects find their pet favorite protocol. gRPC is a great example of a heavily abused favorite protocol now because, hey, it's fast. Yeah, it's fast, but it has trade-offs. Yeah, but it's fast. Yeah, but there are trade-offs. Yeah, but it's fast. Okay, yeah, well, yeah, it's fast. You're right. It's fantastic. But it also, in its default way, creates really tight coupling between two things. Tight coupling between parts of your architecture creates brittleness. So we need to talk about two kinds of coupling here. Semantic coupling and implementation coupling. Semantic coupling is the nature of the problem that you're trying to solve. So if I'm ordering a book, I have a catalog, I have a customer, I have inventory, I have shipping. That's the semantic coupling of that workflow. And if we decide now, we're going to start selling widgets in addition to books, nothing in architecture is going to prevent me from having to change my system because I'm changing the thing I'm writing about. What architecture can help you prevent breaking are implementation coupling, where you've tied implementation details too tightly together. This goes back to that bounded context idea. And this is what happens all the time between architectural boundaries where you go, default protocol is gRPC. Well, gRPC defaults to map everything to everything else, whether you're calling all of those things or not, or actually using them or not. That's stamp coupling. So now I've wired these things together. I used the first 3 fields in this call, but I've wired all 10 of them together. Now field 7 changes, and I've broken the contract even though the caller didn't care about field 7. I've overspecified the contract. I've created brittleness in my architecture. What we're really trying to avoid is I make a small change here and I get this rippling side effect. That is the opposite of evolutionary architecture because there's no predictability there. You can't make changes with any confidence. I'm a consultant, so I get to see a lot of pathological cases. I saw a customer at one point, one of our clients, who had opened up a table as an endpoint in their integration architecture. And then they were mystified at the fact that they would change a datum in a table somewhere and like 12 systems would break. And they're like, wow, this is incredible. This is not good. And we're like, yeah, you're right. This is not good. You've opened up the most minute implementation detail and made your entire architecture dependent upon that. No wonder it's fragile and you make a change somewhere and everything breaks. There's no anti-corruption layers. There's no blast radius to keep those changes from expanding. And so that's the whole motivation of bounded context and anti-corruption layers in DDD, is to cut down on intra-service coupling. And it's fascinating that we bring this up a little bit in the book, and you talk about Connascence. That came from the book, What Every Programmer Should Know About Object-Oriented Design, which sounds like such a promising book. It's like, wow, that sounds awesome, but it turns out it's not. Because it was written in 1993, and everybody and their brother in 1993 was trying to build a brand new object-oriented analysis design process methodology. That's why a few years later they created the UML, the Unified Modeling Language, to try to pull all those things together. And most of every object-oriented programmer should know book is about this object-oriented analysis design framework that nobody outside the author and 3 people ever used. But he also defined connascence in that book. But the other fascinating thing he defined in that book when he was talking about connascence is he talked about locality, coupling and locality. And he said, in essence, that it's okay for things that are really close to one another to be highly coupled, but the further apart they are, the less coupled they should be. That was in 1993, and people read that and went, Okay. And then 10 years later, Eric Evans said, oh, and we're calling that a bounded context. And everybody's like, yes, that's it. That's the secret. We've unlocked the secret to architecture. But he had discovered that more than a decade earlier. He just didn't have the right words to say it. But it's exactly the same thing, that implementation details can be tightly coupled, but the more you let that level of detail leak, the more brittle your architecture becomes. And that really is the insight in evolutionary architecture. The brittleness is the thing that makes it hard to evolve, because if you make a small change somewhere and it has unpredictable side effects, you're not going to make that change. And it prevents you from being able to do the mechanics of evolving a system.
You mentioned, oh, go ahead, Nathan.
Oh, I was going to follow up with one of the other new ideas to me in this book that was orthogonal coupling. And this was interesting because I'm doing platform engineering, and we do a lot of this, trying to make it easy for microservices to have a consistent way of reporting to observability layer. Again, the book brings up the idea of sidecars. If anybody works in the Kubernetes world, I'd love to hear a little bit about how the whole idea of orthogonal coupling and that observation came to be.
Well, it's even deeper than that now, because what I've realized is that, I don't know if you were ever familiar with aspect-oriented programming, but that's really aspect-oriented distributed architecture. So aspect-oriented programming in object-oriented systems, this is commonly used for logging. So logging is a great example of a cross-cutting concern. It has nothing to do with my object hierarchy. It's something that just every method should support, is logging. And so aspect-oriented programming were a whole bunch of tools and frameworks where you could create what are called point cuts. And a point cut would basically say, every time right before you call this method, call this other method to generate log information. That was basically the aspect-oriented programming frameworks and what they did. But the purpose of those, that was an implementation. The purpose was cross-cutting concerns across a hierarchy. So fast forward to microservices. We really want to keep the domain concepts highly decoupled. But there's some parts of that system we really need to be highly coupled. Monitoring, logging, authentication, authorization, service discovery. We can't let every team implement their own version of that because we have no consistency. We can't let each team own the life cycle of the monitoring tool, because what happens when we need to rev to the next version? How do we coordinate that? And so that's this idea of a sidecar and a service mesh. The service mesh, if we can assume that every single component has a consistent sidecar component in it, then we can build an interface that talks to all of those and now control monitoring and logging and those kind of things at the architecture level without touching the coupling that exists across the domain, passing customer and sales information and catalog information. And so it really is a way of building cross-cutting concerns in an architecture which are operational. But it gets even better. So it really is aspect-oriented architecture. That's exactly the basis for the concept of data mesh. It takes that concept of orthogonal coupling and moves it to operational versus analytical data. Now, you can't have a sidecar for data mesh because it would have to query the operational database, and you don't want to do that operationally. And very often, analytical data is in a different format. So data mesh actually defines this idea of a cooperative quantum, another service that is a kind of a side service that is tightly coupled to the operational service, but it collaborates in the analytical space, whereas the operational one deals in the operational space. That's another mesh. It's a data mesh. And notice again, it's a cross-cutting concern where the only join point in the architecture is the operational data feeding the analytical data within that data sidecar. That's what is called a data sidecar in that world. There's an even newer version of this, and this is the first time we've talked about this in public, actually. So you're getting a scoop. Mark and I are working on what we're currently calling Book.next. We don't know what the title is going to be yet, but we've got a pretty good idea of what's going to be in it now. And one of the things that we're starting to talk about toward this idea of evolutionary architecture is a governance mesh. So governance is yet another cross-cutting concern over the distributed architecture. So what a governance mesh would do is say guarantee that every service in this architecture is supporting the same level of observability. Once I have that as a substrate, I can build a whole family of fitness functions. For example, so one of the things that we tell people is don't rely on the ability to download tools because your architecture is a magic snowflake that nobody else has, but you can build your own tools to do things. So for example, I want to know if these two services are talking to one another because I don't want them to talk to one another. Well, there's no framework that I can download to check that. But the question you have to ask yourself is the information I care about available? Yeah, the services know who they talk to. And so make them emit log information about who they talk to. And now I can write a three-line script in Ruby that looks at that and sees if they're talking to who they shouldn't talk to. That can go in the governance mesh. And so if you can impose observability on every service, suddenly there's a level of data about the interactions that are there that is queryable. It's available to write fitness functions and other governance stuff for. And so what we're working on now is what is exactly the components of a governance mesh, just like a service mesh and a data mesh. What would the components of that look like? And if you had these three bits of information across your entire ecosystem, what kind of sophisticated fitness functions could you build for that? So and it's only recently that I realized that this is really aspect-oriented architecture, because I did aspect-oriented programming. That's really the basis of Spring. Some of the early implementations of Spring were done with aspects, and that was an old programming thing. And I recently just had sort of the epiphany, wait a minute, the whole service mesh and data mesh thing, it's an implementation of aspect-oriented architecture. And it has interesting legs because it turns out when you build distributed architectures, it's quite often that you have cross-cutting concerns that you'd like to implement, and this is the technique and the mechanism to do that.
One thing I love about the book is it almost serves as a bit of a history lesson. We found that in Fundamentals too, where you talked about some of the older, kind of more monolithic architectures, and newer developers might be like, "What, were they stupid? They just couldn't figure it out?" You say, "No. It's licenses were expensive. It's kind of before the rise of open source software." And so, with those technological developments, we've moved to an entirely kind of new way of doing architecture these days. Do you see anything like that on the horizon? Do you see any sort of macro technological changes that are happening that might influence the way architecture is being built, or uncover entirely new architectural patterns in the future?
Not only do I see that, I see it constantly. It's always a moving target. Cloud is the thing that's disrupting everything in ecosystems right now because you think differently about cloud. This is one of those get off my porch moments. I used to have to build systems that were actually scalable and elastic with physical infrastructure and figuring out all the servers. And now it's a configuration setting on your cloud.
Yeah.
That's just annoying to those of us who fought through all the battles. But it's the exact same thing that I used to get lectured about memory management from old school developers. We used to have 4K and we learned to love it. And, it's the exact same kind of ranty stuff. But it's really just an indicator of the fundamental premise of the evolutionary architecture book. It's never going to stop. It's never going to stop evolving. I don't know what it's going to look like 5 years from now, but I guarantee it won't look anything like it does now. That's about the only thing I can guarantee. And the cloud has been hugely disruptive because we saw this, come in to begin with, and the kind of gentle usage of it, and now it's pretty much everywhere in some form or another. And this. So this is a reactionary world because the cloud vendors. So the cloud vendors really want you there forever. And so they're doing everything they can. They want that subscription model. Microsoft realizes it's a terrible idea to sell software with updates because at some point you don't want the updates anymore and they don't get money anymore. If you sell a subscription, you've always got cash flow. So that everybody is doing that model. And so cloud is going to be pervasive, and they're going to keep leapfrogging each other in terms of capabilities. And it's quickly going to become, sort of commoditization, but that's going to open up a whole new level of abilities. The ability to do AI at all these different levels. So you have large language models that run on clouds, but we now have small language models that run on phones. Apple is putting an enormous amount of effort into hardware-based, device localized, and that's going to open up all kinds of interesting capabilities from both an architectural standpoint and probably headache. So the AI and cloud together, I think, are going to be the things that are going to dominate our thinking for the next short term until, the next major thing comes along. But that's always the way, nobody went to an ivory tower and planned for microservices. The way that came about was the architecture kept changing, and clever architects noticed it's like, hey, well, look at that thing. Oh, well, if we took that new thing and put it together with that new thing and kind of wound it up, that would solve this problem we've had forever. And other people look at that and look at what they did. Hey, we could do the same thing. And at some point, it's like, we got to come up with a name for that thing that we just did. Let's call it microservices. There will be another architecture that will supplant microservices at some point. We don't know what it'll look like yet, but it will be based on the kind of synergistic combination of new features that kind of creep up and then synergistically join together. And it's impossible to predict those things, which is why it's so fascinating. It really is kind of like biological evolution, because it's really hard to predict what, this thing will change that, and this will, but then that'll, and so it's really hard to get any kind of, deterministic predictability about the thing. But that's the essence of software. If you build fast feedback loops, you don't have to predict it. You can adjust to it as it changes. And so that's the essence of this idea. I talked to a client at one point in a mining company, and he said their biggest problem was convincing their management that software systems couldn't last for decades. Because when they built mining equipment, they literally amortize it for 100 years. So when they buy something, it's bought. And, they're saying, what do you mean you need new servers? We bought you new servers 10 years ago. Why can't you use the... And they were having a real hard time. It's just a fundamental different nature. So software is always going to keep changing, and even the rate of change, I think, keeps going up. And the AI is just going to make that, just exacerbate that. But hey, it's good job security. So here's an interesting kind of sort of meta question that you can think about. Has there ever been a time in history where people have taken so much detailed knowledge and learned it so well only to flush it out of their brains and replace it with a whole bunch of other detailed knowledge? The first programming stack I ever worked in was this language called Clipper. I know everything there is to know about Clipper, and it does me absolutely no good whatsoever now. I'd like to dump all that stuff out and replace it with something useful, but I can't. But how many times have you taken your entire knowledge base and dumped it out of your head and replaced it with another one? And has any group of workers in history ever done it as much as computer programmers have done in the last, several decades of rapid breakneck evolution in our space? It's a fascinating intellectual question to think, has anybody ever gone through as much intellectual churn as we have in the software world?
It's funny when you talk to people outside the industry or people considering the industry, because I find that to be a good kind of, like I said, meta question to ask people and say, I basically say, you're not going to be able to get good at this like once and then kind of do that for the next 40 years. You need to continuously learn. And to some people, that's really, really exciting. And they make excellent engineers. And there are a lot of other people where they think, oh my gosh, that sounds like the worst career in the world. I remember talking to a friend and then being surprised when I said, I'm like, every day I show up to work and I'm not quite sure what the problem is, or like I know what the problem is, but I don't know what the solution is. Like a lot of my day is just researching and figuring stuff out, and that was so foreign to them. So yeah, I like how you say, like, has any other group of workers ever just kept flushing knowledge out? And probably not. I can't think of any.
I mean, maybe some sort of scientific discipline, but we're engineers, so we'll drop something in a heartbeat if something better comes along. So we have no loyalty to bad things at all. So
I mean, it wasn't until right around the year 2000 that we actually observed a supermassive black hole. So I think that even like physics has no safety, right? With the first gravitational wave observed, like they're doing the the rate upon which they're having to rewrite what foundational physics is also increasing. So that's
well, in biology too. I brushed up against some biology when I was in university, and it has become a computational science in a massive way over the last few decades, and it's really completely transformed that science. So
fascinating.
I have a friend with a PhD in math, but kind of like tangential to biology, and she was just talking to my wife about how she's had to start learning a lot of programming just to pull it off.
Yeah.
Yeah.
I think we're going to see many, many more of these synergistic hybrid roles, programmer / biologist, physicist, because at some point you're going to need the skills that a programmer has, but you also need the deep problem solving skills of that specialization as well.
How will we maintain our air of superiority then?
Oh, there'll always be priesthoods. Well, there'll always be some people who are using Emacs rather than VI and can feel superior to other people because of that.
Love it.
Tabs versus spaces.
Exactly.
Well, thank you so much for coming on, Neal. Before we wrap up, is there anything you'd like to plug for our audience? Anything you're working on? Even just any books you've been reading that you think our audience should check out?
I've been reading. I recently read the Team Topologies book, which is one of the reasons I brought that up. It's a great book. I've actually been reading some stuff around LLMs and that kind of stuff now because that's what the current fad is right now. And composer biographies. I love composer biographies. I'm reading Beethoven right now. Great book by Jan Swafford on Beethoven, his fascinating life. The thing I'm working on right now is, from a writing standpoint, Mark and I are working on Fundamentals of Software Architecture, 2nd edition.
Yes.
And we're actually surprised at how much we're able to add. There was very little about cloud in that book. We're adding a chapter on modular monolith and a stronger distinction between styles and patterns and that sort of stuff. But we're also, I probably mentioned this before, Mark and I write books iteratively. So we take a seed of an idea and then iterate on that idea. And we're very much in the very active iterative phase of what we're calling book.next right now, which is very exciting because it's brand new stuff. I've been starved for new stuff a little bit lately because after we wrote Software Architecture and Hard Parts, I went back and did Building Evolutionary Architecture 2nd edition, which is a revisit. And then we did Head First Software Architecture, which is a revisit from some of the subject matter from the Fundamentals book, but written sort of as a graphic novel. So it's really cumbersome to write Head First books. Like, you cannot believe how cumbersome it is to write Head First books. But that was sort of the same subject matter, and now we're doing the Fundamentals book, 2nd edition. So it's actually quite exciting to be building brand new IP, and we're aggressively building some new stuff that we're super excited about. So just like you love to come in and problem solve every morning, I love to sit down and say, okay, how can we figure out how to do this thing now from a writing standpoint? For me also, the big conference speaking session's about to kick in Europe. So I'm going to spend most of the fall in Europe in one place or another, speaking at all the conferences there, because none of the European conferences happen in the summer because everyone's on vacation. So they all happen in the fall and the spring. So.
And I'm going to fly there so I can bump into you at a coffee shop.
There you go. Hey, there's a good chance if there's a place that sells strong espresso near the conference venue, you'll find me there. So.
Well, thank you so much for coming on, Neal. Again, everyone, it's Building Evolutionary Architectures by Neal Ford and his many other talented co-authors. We had a great time reading it. There's a link in the description if you'd like to check it out yourself. As always, you can find us at Book Overflow Pod on Twitter. On YouTube, we're at Book Overflow Pod. You can find Nathan's other work at functionallyimperative.com. And you can find me on Twitter at Carter Morgan. And Neal, are you active on Twitter or Facebook or anything like that?
Yep, I am at NEAL and the number 4D. So Neal Ford on Twitter.
I've seen that and I'm jealous of that handle. You can't make anything fun out of Carter Morgan.
There's a little bit of a funny story behind that too, because when Twitter first came out, I got my name, which is a nice 8-character name, Neal Ford, but nobody else is on Twitter. So it's like, well, this is kind of a dull. But then everybody got on Twitter and it's like, oh, I need to get on Twitter. And I checked my name. It's like, somebody's already got it. So I did the Neal 4D thing. And literally like 2 years later, I was driving along. It's like, wait a minute. I know who got my name on Twitter. It was me. But by that time, everybody was using the new handle. So I just went and canceled the other one.
That's me on Reddit. I know that I have the Carter Morgan username on Reddit, but I don't remember the password, and it's like hooked up to an email, and so I'm Carter D Morgan on Reddit. You can find me on various subreddits. Well, thanks so much for tuning in, everyone. Thank you again, Neal, for coming back. We really appreciate it, and we hope you enjoyed the interview.
Yep, absolutely. Thanks for having me.
See ya.
See ya.